Hey everyone, and welcome back to The Explainer. So today, we're stepping right into a masterclass on some of the absolute most fundamental concepts that govern our entire physical universe, work and energy. Whether you're pushing a broken down car, lifting a ridiculously heavy box, or just watching something speed up right in front of you, what's actually happening behind the scenes? Well, today, we're going to unpack the pure mechanics of motion.
Okay, let's dive into this. Here is our roadmap for today's masterclass. First, we'll prep our mindset for learning. Then, we'll hit the energy roadmap, define what physical work actually means, unpack kinetic energy, and finally, bring the whole shebang together with the work-energy theorem.
All right, starting with part one, a mindset for learning, preparing for physics. Because honestly, getting your head in the right space is just as crucial as the physics itself. So, we are jumping right into week 5 of an established physics syllabus here. I want you to just imagine you're sitting in a huge lecture hall right now. It's the middle of the term, the concepts are getting heavier, and we're making that big transition from just observing basic motion to actually understanding the deeper mathematical reasons why things move the way they do. And to really tackle this hard science, we can look at how the source material beautifully grounds this academic journey. The presentation actually opens with a dua, a prayer for focus. It says, "Berdoalah kepadaku, nescaya akan kuperkenankan bagimu." It totally encourages a moment of pure intention before the lecture even begins. You know, taking a breath and setting our mental focus before we dive into the complex mechanics ahead is just a fantastic reminder that true learning requires a highly present and focused mind. So, with our minds primed and ready to go, let's transition to section 2, the energy roadmap, and exactly what we will achieve. Our targets for today are pretty crucial. By the end of this explainer, you're going to know how to perfectly define work done in a strictly scientific context. You'll differentiate between positive, negative, and zero work, define kinetic energy, and ultimately apply the incredibly powerful work-energy theorem to solve problems. That is our target. Let's hit it.
Moving to section 3, defining physical work. And like I said, we're going way beyond the everyday meaning of the word here.
We're focusing squarely on work done by a constant force. See, in everyday language, reading a massive textbook or sitting at a desk thinking really hard might definitely feel like work. But in physics, work isn't just a job or that feeling of pure exhaustion. It has a very strict, mechanical definition that specifically involves a constant force acting on an object over a distance. Right, so the absolutely crucial point here is that physical work done is calculated by the force applied to an object and the resulting change in its position. And here is where it gets kind of counterintuitive for a lot of people. Work isn't just a single accumulating amount. Depending on the direction of your force compared to the direction the object is actually moving, your work can be positive, negative, or even zero. Think about it. Pushing a box forward, yep, that's positive work. The friction pushing against that sliding box, that is negative work. And pushing as hard as you possibly can against a solid, immovable brick wall, that's zero physical work. Literally zero. I don't care how much you sweat. Now that we've totally redefined work, let's transition to the second major component of our masterclass with section 4, kinetic energy unpacked. This is the energy of motion. Let's just strip away all the visual clutter and math for a quick second and focus entirely on the pure definition. Kinetic energy, which we usually just represent with the letter K, is defined simply as the energy of a body due to its motion. Meaning, if an object is moving, it has kinetic energy. Period. If it's completely stationary, its kinetic energy is absolutely zero. It's the raw, active currency of movement. And this equation right here brilliantly illustrates the mathematical reality of that motion. K equals 1/2 mv squared. This tells a very specific, amazing story about the direct relationship between an object's mass, its speed, and its energy. So the m stands for the mass of the object, right? And v is its speed. But notice that the speed is squared. This is huge. It means if you double the weight of a moving car, sure, you double its kinetic energy. But if you double the speed of that car, its kinetic energy quadruples. The energy of motion scales so dramatically with speed. And that's exactly why high-speed impacts carry so much more devastating force. All right, so we've got our two distinct puzzle pieces now, work and kinetic energy. Let's build up to the big climactic reveal in section 5, the work-energy theorem. This is where we mathematically unite force and motion. So imagine a block with a specific mass, let's call it m, sitting on a completely frictionless horizontal surface. If a constant net force, like a solid push, acts upon it, it undergoes displacement. Because we're exerting a force, and the block is actively moving as a result, we are officially doing work on it.
Let's see how this builds from the absolute most basic laws of physics right up to our grand conclusion. We start with Newton's famous second law, force equals mass times acceleration, right? Well, when we apply standard equations of linear motion to that accelerating object and then mathematically substitute them back into our force equation, boom, we can calculate the exact change in the object's kinetic energy.
And that beautiful derivation leads us straight to this profound conclusion. The work-energy theorem formally states, the work done by the net force on a body equals the change in the body's kinetic energy. If you want to change how fast something is moving, you absolutely must do work on it. The mechanical work you put in perfectly equals the change in energy that comes out. They are literally two sides of the exact same coin.
Now, we've looked at this concept today through the lens of a perfectly frictionless surface, just to understand the pure theorem, but that leaves us with a really provocative puzzle based on our earlier syllabus. If work exactly equals the change in kinetic energy, what happens to that energy when a non-conservative force, like friction, enters the picture? I mean, where does the energy actually go when a sliding block eventually grinds to a halt? Think about that for a bit, because it's the ultimate gateway to understanding energy conservation, which is exactly what we're going to tackle in week 6. Until then, keep exploring, and thanks so much for joining me on The Explainer.